Hey everybody, this is presentation 2 for data 670. My name is Evan Moskowitz and here we go. First, I start with an introduction where I outline the entire project. This includes the analytics used and what credit card default is. Then I'll move on to consequences of default, how it affects people and credit card companies. Then data and tools, where I cover the data set and the software that I use to analyze the data. Preliminary analysis, where I generate descriptive statistics and go over that. The primary analysis, where I actually build the statistical models and generate inferential statistics. And I'll finish off with the conclusion, where I go over my findings and some recommendations. Part 1. Introduction. The problem. All over the world, individuals default on their credit card payments. This causes issues for both cardholders and credit card companies. So what is credit card default? Well, credit card default occurs when a cardholder fails to pay off his or her credit card balance by the given due date. And why is this bad? Because default puts a credit card company's revenue at risk, and businesses do not like to lose money. So the solution: in order for credit card companies to reduce the rates of customer default, they have to weed out unreliable applicants. And to weed out unreliable applicants, credit card companies need models and insight that tell them who is likely to default. To build statistical models and generate insight, we need to analyze data on credit card customers, which is what this project is about. The overall goal is to use data on credit card default and cardholder attributes to build statistical models that tell credit card companies what applicants are likely to default in order to reduce customer default rates and increase revenue. It's a long sentence. Alright, the analytics process is a continuous cycle. So here we have it outlined. It starts with data collection, where organizations put together data, turning unstructured data into structured data. Then they analyze the data and build models, which makes them insight. They use this insight to develop strategies that optimize their business, and then they integrate these strategies and start over. This project uses data from the UCI machine learning repository. The data is on credit card default in Taiwan, and it came from a survey of cardholders in 2005. I took the original dataset and modified it some, turned it into the CCD, it stands for Credit Card Default dataset. The CCD dataset contains 9 attributes and 30,000 observations, and I'll go over later how I modified it and why. Okay, the methods. To generate statistical models on credit card default, we run the data through machine learning algorithms. And here I have the specific algorithms listed: k-nearest neighbors, decision tree, logistic regression, and the neural network. Each one provides a different way to look at the data. Alright, the tools. To calculate descriptive statistics and run machine learning algorithms, I use 4 analytics software platforms. Those are Watson Analytics, Tableau, RapidMiner, and SAS Enterprise Miner. Now I'll go over what I like to call the credit card cycle. This starts with spending. People want stuff and they have a credit card and they might spend more than they have because it's so easy, and then they get the bill and they're not able to pay it, so that leads to default. When they default enough, then debt starts to mount up, and if people don't pay off their debt, then collection agencies will start to go after them to collect the stuff back. And then that could lead back to spending because the people think they're out of it, but then they want stuff again. So it leads back to spending, and it's just a vicious cycle. Alright, so that was the overview of the analytics process and credit card default. Now I'm going to go into specific consequences of credit card default. For credit card companies, default puts revenue at risk, while for credit card customers, default puts lifestyle at risk. Once they default, it gets harder to buy stuff, and these people who are buying so much, they're used to a certain lifestyle. They're not very happy when they can't get that lifestyle anymore. Defaulting on credit card payments can impact cardholders in far-reaching ways. The severity of punishment depends on the severity of default. The more time that passes and the more money owed, the harsher the punishments become. So it's in people's best interest to pay off their bills as soon as possible. So when people default on their credit card bills, the companies send negative statements to the major credit bureaus, and this causes these people's credit score to decrease, their interest rate to increase, and it becomes harder to obtain loans and additional credit cards. Accumulation of debt leads to collection calls and mail. It can lead to litigation where the credit card company actually sues the delinquent cardholder, and it can also result in tax complications. Also, too much debt, and then utility companies will require deposits because they don't trust these people, can cause insurance rate increases because you're seen as not responsible, and also loss of employment opportunities because employers don't want to hire people who are having these issues. It just makes things complicated for them. Default also can lead to health issues such as stress, depression, and sleep loss. Money is a big worry, and you don't have it, you start to get upset. A national survey commissioned by creditcards.com found that 6 out of 10 adults report losing sleep over financial trouble. So 60% of the adult population. A 2013 study by Northwestern University found that higher debt is associated with poor physical and mental health. Individuals with higher debt-to-asset ratios were found to experience more stress, more depression, worse general health, and higher diastolic blood pressure. So the penalties for cardholders are quite severe. Now let's see how credit card companies deal with default. When faced with a high rate of customer default, credit card companies used to raise interest rates on reliable customers to make up for the revenue loss. Essentially, these companies would punish good customers for the actions of bad customers. So they have customers they know are going to pay, so they just raise the interest rates to make up for the ones who aren't paying. Of course, no good deed goes unpunished. Luckily, this practice came to an end in February 2010 with the CARD Act. Stands for Credit Card Accountability, Responsibility, and Disclosure. The CARD Act instated ethical boundaries that made it more difficult for credit card companies to raise interest rates. Now today, most credit card companies deal with customer default in a similar fashion. I'm going to go through the stages. First, the company will attempt to reconcile the situation with the delinquent cardholder by repeatedly contacting him or her via phone and mail. If that doesn't work, the company will hire a third-party collections agency to continue the campaign of phone calls and mail. And this actually costs the company money because they have to hire these agencies to work. The companies might end up selling the debt at a highly discounted rate. In this case, the company makes some of its money back but loses most of the potential revenue. Another possible outcome is the company actually sues the defaulting customer to bring him or her to trial. If the company wins, it may be able to take money directly from the cardholder's bank account or garnish wages until the debt is paid off. So far, we focused on credit card default in the USA, but there's credit card default all over the world, and in particular, the data that this project uses deals with credit card default in Taiwan. All right, this is part 3, data and tools. Now I'm going over data preparation. The original dataset came from the UCI machine learning repository and was titled Default of Credit Card Clients.xls because it was an Excel spreadsheet. This dataset was a result of a 2005 survey of credit card customers in Taiwan. It contained 24 attributes and 30,000 observations. For this project, I modified the original dataset as follows. First, I renamed the dataset to CCD for credit card default and converted the file format to .csv, which is comma separated value. And I did this just because it makes it more compatible with analytics software. It's much easier to import and deal with. Next, I altered the variable names to all caps and removed spaces and special characters. Again, I just did that for an easier data import. Then I checked for missing or mislabeled entries and replaced any values for these. And last, I created new variables by aggregating columns together, and then I removed the original columns. The target variable, also called response or dependent variable, is default. Default is a binary variable that takes on a value of 1 if a customer defaults on a credit card bill, or 0 if the customer does not default. Here's a list of the input variables. Here's a table for variable definitions. So it lists the name of the variable's role, the type, the description, and the parameters. I already went over default. Credit represents the customer's credit card spending limit. That's an integer for New Taiwan dollars. Sex is the customer's gender, where 1 is male, 2 is female. Education is the customer's highest level of educational attainment. Marriage is the customer's relationship status. Age is the customer's age in years. History average is the customer's average payment delay length from April to September of 2005. Bill average is the customer's average bill statement amount. And payment average is the customer's average payment amount to the company. I'm going to go over variable creation. So each of these attributes was spread across 6 variables, where each variable represented a different month from April to September of 2005. To streamline the data, we took the average for each set of 6 columns and created the new variables below. And here's a screenshot of Excel during this process. Data cleaning. The original data contained no missing entries, but certain variables did contain mislabeled entries. For example, education should only have values ranging from 1 to 4, and it contained 0 and 5 values. So there's a screenshot of Excel that shows the find and replace method I used to clean up the data. And what I did is I just replaced the mislabeled entry with the closest value. So if there was a 5 for education, I put a 4. If there was a 0, I put a 1. And the same for the other variables for marriage and history. Here's a table for the analytics tools used during the project. So Watson Analytics and Tableau I used for the preliminary analysis to assess the quality of the data and to produce descriptive statistics. RapidMiner and SAS Enterprise Miner I used for the primary analysis, where I generated the statistical models that are listed there. Alright, now we're going to go over the preliminary analysis. This stage of the experiment involved using Watson Analytics and Tableau to assess the CCD data and generate descriptive statistics. Descriptive statistics describe the actual sample of data, and here I have a table where I list the common ones for central tendency, dispersion, and relationship. The first thing I did was use Watson Analytics to assess the quality of the CCD data, and as you can see, Watson gave the dataset a quality score of 65, which is an average of all the quality scores of the variables. Watson found that there are 5 variables with outliers in the dataset. Age and credit have some, but bill average, history average, and payment average have in the thousands. Because of these outliers, the variable distributions are skewed positive, which means their tail trails off to the right. And because the skew is positive, this indicates that the outliers are in the upper end of the spectrum. This makes sense considering global wealth inequality. As you can see, the top 0.1% has much more income than the rest of the population. This means they're outliers who skew the distribution of income to the right. Watson produced a list of top field associations. This just illustrates correlation between certain pairs of variables. For example, payment average and bill average are positively correlated, which makes sense since customers with bigger bills have to pay more. Watson also produced a list of top influencers of default, and according to Watson, history average, payment average, credit, and education are the best predictors of default, and they all have around the same predictive strength at 78 or 79%. With Tableau, I produced box and whisker plots for the numerical variables. These box plots illustrate overall dispersion, including range, outliers, and the median. With the box plots for bill average and payment average, it is very obvious that there are a lot of outliers and that the skew is positive. As you can see, all of the observations on the right kind of skewing the distribution. I also used Tableau to produce bar graphs for the categorical variables. The default rate in the CCD data is about 22%. In terms of marriage, more individuals are single, but there's still plenty of married people. In terms of education, most topped out at the university level, but a good amount went to graduate school. In terms of sex, most of the survey respondents were female. Now we're moving on to part 5, which is the primary analysis. This section consists of running machine learning algorithms on the CCD data to build models that predict whether or not a customer will default. Before we start the analysis, we'll go over some inferential statistics which allow us to generalize results from a sample to the population at large. So there's hypothesis testing, which is framing an experiment in terms of two hypotheses with the goal of rejecting or not rejecting the null hypothesis. The null hypothesis states that the effects are not statistically significant, while the alternative hypothesis states that the effects are statistically significant. This table has a lot of information, but what's important to know is that the software will provide p-values. If these p-values are less than our significance level alpha, then we can reject the null hypothesis. Here we have the hypothesis test for the experiment. The null hypothesis is the CCD independent variables have no significant effect on credit card default in Taiwan. The alternative hypothesis is the CCD independent variables have a real effect on credit card default in Taiwan. And I've chosen alpha of 0.10. The results of the models will tell us whether or not we can reject the null hypothesis. K-nearest neighbors is a simple model that makes predictions based on pattern recognition. It classifies observations based on the majority vote of their k-nearest neighbors. K is an integer that is chosen by the experimenter. The second model I made in RapidMiner is a decision tree. The decision tree is a visual model that uses nodes and branching pathways to illustrate the effects of independent variables on a target. It consists of leaf nodes, which represent the independent variables. These are ordered in a hierarchy in terms of explanatory power. The terminal node or dependent variable relays the outcome. So the first thing I did with RapidMiner was import the data, and here's a screenshot of part of the import process. Here, RapidMiner allows you to choose the data type for each variable. Once the data is imported, RapidMiner automatically produces summary statistics. As you can see, each variable has a graph that illustrates its distribution and also has other parameters such as the minimum, maximum, average, and so on. This is the process diagram I used in RapidMiner for this project. Each box is called an operator. Each operator carries out a different function. The first operator retrieves the CCD data, then the data moves into the correlation matrix operator, then it goes into the setRoll operator where I can assign which variable is the target. Then the data goes into the multiply operator where it is duplicated and sent to two different validation operators. Each one of these contains a model subprocess. Then finally both models' outputs go into the ANOVA operator for comparison. So here's the correlation matrix for the credit card survey data. The correlations are consistent with the Watson field associations from earlier. And here we have the subprocess of the first validation operator. This is where I ran the k-nearest neighbors model in the training section. In the testing section, I applied the model to testing data. That is to assess how good the model is at predicting default, which of course is done with the performance operator. So here's the output for the k-nearest neighbors algorithm. RapidMiner provides a summary of the model. I set k to 5, which means that the model classified observations according to their 5 closest neighbors. The performance operator generated the confusion matrix you see before you. This matrix provides a rundown of how the k-nearest neighbors model predicted default. According to the class recall and precision, the model had more difficulty predicting outcomes of default compared to outcomes of no default. This makes sense considering there were a lot more observations of 0 than 1, which means that the model had a lot less material to learn from in the cases of actual default. Overall, the k-nearest neighbors model had an accuracy of 74.75%, which is pretty good. This means that the model was correct about 3 out of 4 times when classifying the test data. Here's the subprocess for the decision tree model. It works exactly the same as the k-nearest neighbors one, so I won't go too much into it. This is the decision tree generated by RapidMiner. I set the maximum depth at 5. This model implies that history average is the most important variable because it is the first leaf node. The critical value it splits at is 0.25. If a customer has an average delay length of 0.25 months or less, it goes to the right. If it's greater than 0.25 months, it goes to the left. The next most important variable is bill average and then age. Interestingly enough, the decision tree predicts that larger bill averages actually lead to outcomes of no default. This kind of makes sense since people with larger bill averages might just have more money, so they can actually pay their bills. The model also predicts that individuals over 55 have a high chance of defaulting. The model also predicts that when bill average is small and the individual is over 55, then that person has a high chance of default. And here's the confusion matrix for the decision tree. As you can see, the model has an accuracy of 80.69%. This means that the decision tree would be preferable to use over the k-nearest neighbors model in this case. To finish out RapidMiner, we have the ANOVA test, which stands for Analysis of Variance. This tests to see if there is a significant difference between two samples or models. Since the p-value is so low, we can reject the null hypothesis, which means that the improvement in the decision tree model over the k-nearest neighbors model is significant. Next up is SAS Enterprise Miner. The first model is regression. That is a model that estimates the relationship between a target and a set of predictors by building a best fit equation. Here I have the functional form for linear regression and a chart explaining what each of the parameters is, but we actually can't use linear regression. Logistic regression measures relationships when the dependent variable is categorical, and since the target default is binary, we will use a logit function to estimate the outcome probabilities. There is a functional form for logistic regression. The second model I built in SAS Enterprise Miner is the neural network. The neural network is a complex model that uses nodes and connections to represent neurons and synaptic pathways in the human brain. This model is so useful because it takes into account the interaction effects between independent variables. Once again, the first step is to import the data into the software, and here is a screenshot of part of this process. In this part I set the role and the data type for each of the variables. Here's the process diagram I used in SAS Enterprise Miner to run the analysis. The first node contains the CCD data. I then split the path so there's one path for each model. Each path starts with a sample node that takes a sample of 80% of the original dataset. This sample moves into a descriptive statistics node, then into a data partition node, into the model node, and then finally the results of the two models are combined into a model comparison node. The stat_explore node produced a worth chart that shows how good each independent variable is at explaining default. According to this chart, history average is by far the most explanatory, then credit and payment average are decently explanatory, education, bill average, and age are slightly explanatory, then sex and marriage are not really explanatory. It's important to note that this worth chart is not a replacement for an actual model. The stat_explore node also produced summary statistics. The top image shows the categorical variables and the bottom image shows the numerical variables. And this output is consistent with the previous descriptive statistics. The data partition operator splits the dataset into 3 different sets for training, validation, and testing. This makes it very convenient to run a model and evaluate the output. The training I set to 40%, while the validation and test I set to 30% each. So here are the results of the logistic regression. What's important to know is that this table contains a list of parameters, the regression coefficients, and the p-values. Most of the attributes have very low p-values, indicating they are significant in explaining default. However, age, marriage, and sex have relatively high p-values, which means they are likely not significant in explaining default. SAS automatically runs a likelihood ratio test for the global null hypothesis. This is testing against the null hypothesis that the regression model is as effective as an intercept-only model, while the alternative hypothesis is that the regression model is effective. And since, again, the p-value is so low, we can reject the null and accept that our logistic regression model is effective at predicting default. Here's the output of the neural network model. Each attribute has an estimate of how it affects default. The goal of the neural network is to minimize the value of the objective function. I set it to run 100 iterations, and it minimized the objective function at about 0.46. Here's a cumulative lift graph of the neural network model, and this measures the ratio of how effective it is against having no model at all. The baseline is represented at y=1, and as you can see, the model is much more effective than not having a model. To close out SAS Enterprise Miner, we have the output of the model comparison node. This output shows that the logistic regression and the neural network models performed about the same. They both had misclassification rates of 20%, meaning accuracies of 80%, and they both had about the same lift. Now we finally reached part 6, conclusion. According to the sample data, the default rate in Taiwan is roughly 22%, or about 1 in 4.5. Credit card attributes seem to be positively skewed, similar to wealth. Many of the explanatory attributes have conflating relationships, which means the independent variables affect each other, such as payment average and bill average and credit and all of those. The attribute that best explains default is by far history average. The next two attributes, credit and payment average, decently explain default. Education and bill average slightly explain default. And age, sex, and marriage appear to have little to no significant effect on default. The decision tree, logistic regression, and neural network models performed about the same with the classification accuracy of about 80%. The k-nearest neighbors model performed slightly worse with a classification accuracy of about 75%. All of the models were found to be more effective than using no model at all. The low p-values of the models were lower than our alpha, 0.1, meaning we can reject the null hypothesis. This implies that collectively the explanatory variables have a real effect on credit card default. To close out the project, we have some recommendations. Since the models have been tested and verified, we suggest that credit card companies in Taiwan integrate the decision tree, logistic regression, and/or neural network models into their organizational structure. Since the k-nearest neighbors model was not as effective, we would recommend not using it. Specifically, we believe the visual nature of the decision tree makes it a good choice for informal customer service use. Employees can have their own decision tree so they can quickly assess whether the customer is likely to default and thus likely to receive a credit card or a certain credit limit. For processing actual credit card applications, we suggest using the logistic regression or neural network model since they are more comprehensive. If the model says an applicant is very likely to default, the company can reject the card application. If the model says an applicant is somewhat likely to default, the company can give him or her a card with a low credit limit. Ultimately, credit card companies can use these models to make better decisions regarding card applications and credit limits. By protecting themselves from individuals who are likely to default, these companies can reduce their customer default rates. In turn, this should increase revenue and reduce expenditures for tracking down delinquent cardholders. While the given models seem to be effective, analytics is a continuous process and there is always room for improvement. The better the model, the more accurate the predictions, and more accurate predictions mean less customer default and more revenue for credit card companies. We think credit card companies should fund additional research into default. This research should lead to more data. With additional variables and more observations, new and better models can be built. So some suggestions for research would be data collection within the actual companies and also online surveys. Some variable suggestions would be lifestyle, income, siblings, upbringing, race, religion, nationality, social media usage, etc. And that is my presentation. I'm now going to hibernate for a long time, and here are my resources. Thanks for watching.